Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're continuing a look at aldehyde ketone reactivity, focusing on the alpha carbons. Last Scribblecast lecture, we examined how the alpha hydrogens off of the alpha carbons are more acidic than normal hydrocarbon hydrogens. Now we're going to examine a chemical reaction referred to as alpha-halogenation. Alpha-halogenation can take place under acidic or basic conditions, and so we're going to examine alpha-halogenation under acidic conditions first. Now I can take any aldehyde and ketone and treat it with halogen under acidic conditions. Let's examine the molecule acetone, and let's react it with X2, where X2 can be chlorine, bromine, or iodine. Okay, so X, if you like, equals ClBr, or I. And we react it under acidic conditions, so we're in acid, H3O plus is present. And what will happen in this reaction is we will halogenate, halogenate the alpha carbon. Now we want to look at the mechanism of reaction so that we can understand how this process actually happens. Reactions in acid occur because of the increased concentration of enol that occurs in acid. We learned last lecture that enol concentration is very small relative to the keto concentration. But if you add H+, you can protonate. And of course, that's resonance stabilized. With a structure, resonance structure that is a carbocation, has a positive charge on carbon. And now there's two lone pairs on the oxygen. So effectively the pi electrons have moved out. Now this positively charged species, right, can displace a hydrogen. So in order to do this, I'm going to draw my hydrogen here. If it loses H+, minus H+ now, from that contributor, you see protonation facilitates the formation of enol. What we have is the enol form of acetone. Now under neutral normal conditions, this molecule is present 400,000 times less concentration than the keto form. However, in acid, you can increase that somewhat. And as the concentration increases, subsequent reactivity of the enol becomes possible. So this step right here is often called enol formation and referred to as step 1 of the reaction mechanism. In actual fact, in acid, it is the enol that is responsible for alpha-halogenation. step 2 is attack of the enol by the halogen. And you should also note that this is a slow step, partially due to the low concentration of enol. So step 1 is our slow step. Let's take a look at step 2. Step 2 is the alpha-bromination itself, and it occurs fairly rapidly. Alpha-halogenation, let's use bromine. So what we have, remember, is our enol. And the enol, we're going to react with X2. In this case, we're using as our X bromine. This reaction, each X has 3 lone pairs, and this one is very fast. Now remember, the oxygen has 2 lone pairs. One of the lone pairs on the oxygen reforms the pi bond. Pi electrons attack the X and the bond breaks. Now remember why this happens. If you recall back in alkene chemistry, we learned that the halogens, such as Br2, are polarizable. That is, as a Br2 molecule approaches the pi cloud of electrons, the large diffuse pi orbitals, electrons, repel electrons in bromine. Bromine's polarizable, and so electrons move in this direction. This induces a delta plus, delta minus in the molecule. This is what leads to attraction and causes the bromine-bromine bond to rupture, producing Br minus and effectively a Br attached to the carbon. Now, in simple alkenes, we often got bromonium, a bridging bromine forming, a bromonium ion. But in this case, because of the reformation of the carbonyl, the positive charge ends up not on bromine, but out on the oxygen. So when this attack is done, you actually form this. Of course, the last step is very fast, and it is a step we've seen that occurs in reaction mechanisms when it is favorable, and that is step 3, deprotonation. It's not really an exclusive part of alpha-halogenation. It's really more just something that happens as necessary. We've seen it in the SN1 as well. So deprotonation of the protonated species, very easy. Again, this reaction is very, very fast. So let's, although I showed the individual steps of step 1, let's summarize step 1, showing the tautomerization, because step 1, remember, enol formation. I'm not going to show all the steps, I'll just draw the equilibrium, was the rate determining step. So once again, enol formation, or the equilibrium, okay, the equilibrium between the tautomers Okay. This was slow. Even in acid, the concentration of enol is small, and this is our rate determining step. So let me pose the question. In acid, under these conditions, oops, left off my X. No, it's there. Is the formation of the product likely to facilitate the attack of another X, or is it likely to slow down the attack of a second X? Do we have to be careful or concerned about, in this case, the addition of a second halogen? Well, in order to answer that, we have to ask, what will the influence of X be on the rate determining step? That is, if we change acetone to CH2X, is the concentration of enol likely to go up in acid or down? Well, one of the first steps clearly in the reaction mechanism in the formation of enol was what? Protonation. All right. One of the first steps was protonation. Let's rub this off. In order to get enol, I had to add H+. What controls the addition of H+? What determines whether H+ is more or less likely to add to the oxygen? Well, it's the basicity of the lone pair on the oxygen, is it not? These lone pairs right here determine the ease with which they get protonated. Now, halogen that we place on carbon is electronegative. Halogens withdraw electrons inductively. This will put more delta plus here. This will increase the delta plus on carbon here, which will reduce the amount of electronegative effect the oxygen can have, the electrons oxygen can withdraw. In other words, if you like, carbon's pulling back on its electrons. This effectively shrinks the lone pairs. As a result, the lone pairs are less basic when there's halogen on it, and less available for protonation. That means the first step is less likely to happen. That means the concentration of enol drops. For when you already halogen. That means this reaction slows down even more. So attack by second halogen is possible, but it's going to be difficult. And if we want to put two halogens on, we're going to have to increase conditions somewhat. Let's look at a real-world example of this. Suppose I start with acetophenone, and I want to get the dihalogen. That is, I want to react it with Cl2, but I want to put two halogens on this. Well, if I use Cl2, I should use excess Cl2, so I'm going to put EX for excess. And I'm going to react this, of course, in acid. If the reactivity drops, what must we do to drive the reaction, not through just one enolization? And notice it's a multi-step process, that you will put one on first. You will make the monochlor first, and then that monochlor will have to form an enol, which will be attacked to Cl2 to add the second, but to make the CHCl2. Well, we can do that if we heat the system to 60 degrees Celsius. That's a significant amount of heat, and you'll get 94% yield. Okay, 94% yield of 2,2-dichloro, 1-phenyl ethan 1-one. All right. So we can take acetophenone, and make 2,2-dichloro, 1-phenyl, ethan 1-one. Okay. All right. Putting on a third chlorine under acidic conditions is just too difficult. And in order to do that, we usually shift and take a look at the reaction under basic conditions. So let's do that now and examine alpha-halogenation under basic conditions. Under basic conditions, we react acetone with halogen, X2. Halogen again can be chlorine, bromine, or iodine, in base. And we get CH3, C double bond O, CH2, X. And again, X equals Cl, Br, or I. Okay. Now, in base, you don't get protonation. There's no proton to add the lone pair. So the mechanism must be somewhat different. Well, it is. Instead of adding a proton to the oxygen, the base comes in and deprotonates a proton off of the CH3. This is because of the increased acidity that we learned about alpha-hydrogens possess because of the neighboring carbonyl. So if we hit this with hydroxide, hydroxide will come in, grab a proton, it becomes water, of course, and you end up with a carbanion. Now the alpha halogen is a little more acidic, of course, and we learned this last Scribblecast lecture, because this carbanion is resonance stabilized. We can dump it in. We can move this guy out. It's resonance stabilized with the enolate anion, where the negative charge is out on the oxygen. Base helps increase the concentration of enolate, just as acid helped increase the concentration of enol. And so this is a resonance-stabilized enolate anion. Okay. This is our slow step. And this is sometimes called step 1. And instead of enol formation, as is acid, it's enolate formation. I'll just put form with a superscript N for formation. So we've got enolate formation here. And let's make a little room. This is X2 and hydroxide. There we go. Enolate formation is step 1. Step 2, which occurs fast, is not the slow step, is alpha-bromination, alpha-halogenation. If you're using bromine, it's alpha-bromination. If you're using chlorine, it's alpha-chlorination. So we take our anion now, react it with X2 or Br2. You can use X's to represent that. Again, you would think the anion would be repelled from the bromine, but because bromine is polarizable, it can induce a delta plus where the negative charge attacks the X. This bond breaks. And when that happens, you go right to your product, the alpha-halogenated, or in this case, if it's bromine, alpha-brominated molecule, and X minus. Now we can pose the same question we asked last time. When you form the product, okay, so this product, what's the likelihood that it will undergo a second attack by halogen? That will do the same process. Base will come in, deprotonate this guy. So let's do that again. A new step 1B, if you like. A second step 1. Now it's on CH3, C double bond O, CH2X. Base comes in. Okay, so HO minus comes in, attacks, grabs the proton. Remember, this step 1 is the slow step, the formation of the enolate anion. This is what determines whether the reaction or the second attack of X is more favorable or less favorable. And so we want to look at the intermediate and examine whether or not this intermediate is more stable, circle, more likely to form compared to the original intermediate. Which is most likely to form? If you examine this, what's interesting to note is we have an electronegative X now attached to the carbon that bears the negative charge. The electronegative X helps stabilize the negative charge by electronegativity. That means there's more likelihood to form this carboanion. That means the intermediate, the slow step, is going to accelerate because of the presence of X. That means it's more likely to happen. What that means is even though it's still the slow step, putting a second X on is faster than putting on the original first X. Oh, wow. Because of this, it's very difficult to stop at this product. once it forms, it wants to undergo a second monohalogenate or a second halogenation, and you get the dihalogen. And then it'll go on. That one would go even faster. Once you got the second one on, you pull another proton off. Oops, that should be just an H as well. Let's fix that. So what will happen is it will go on even faster. So as you add more electronegative halogens, the process speeds up. So clearly, basic conditions are different than acidic. In acidic conditions, attack by second halogen was difficult. The reaction slowed down. But under basic conditions, the reaction speeds up. Now, because of this, producing just the monohalogenated product, this guy, producing this molecule, is very difficult under basic conditions. Controlling and stopping the reaction with only one halogen attack, it's possible, but it's not very synthetically useful because it's difficult to control. And so if you just want one halogen on, you use acid. But if you want to pick the substitution right through to 3 halogens on the alpha carbon or beyond, and we'll look at the or beyond in a moment, then you use base conditions, and we'll be looking at that. Of course, there is one set of conditions we really need to examine, and that is neutral. You've got acid, base. What about neutral conditions? Well, under neutral conditions, the concentration for step 1 of H+ is low. As a result, the equilibrium shift by adding H+ and protonating is small. Likewise, the equilibrium shift to deprotonation by base to form the anion is small. Because these two effects are less likely to happen under neutral conditions, the concentration of the enolate and enol in solution is much smaller under neutral conditions because the availability of protons and hydroxide is much reduced. This concentration of enol and concentration of enolate being so reduced that under neutral conditions, alpha-halogenation essentially does not occur. All right. But there is a consequence to alpha-halogenation under basic conditions that we really need to look at in more detail. And that is the ability under basic conditions for the halogenation to speed up and add more alpha halogens, and the effect that has on molecules that are methyl ketones. And so what we want to do is look at what is called the iodoform reaction of methyl ketones. And if we examine a ketone, like I'm going to put CH3, CH2, C double bond O, CH3, 2-butanone. And we react this with 3 I2s and hydroxide and base. We'll go right through to the propanoate anion and the molecule CHI3. Now, CHCl3 is chloroform, CHBr3 is bromoform. This molecule's iodoform. That is its common name. Triiodomethane. It is a yellow solid, so CHI3 will precipitate out as a solid, and it's in aqueous solution. It forms a yellow precipitate, yellow solid. Okay, how does this form? Well, in base, remember halogenation speeds up. So step 1, we're going to call repetitive, if you like, repetitive halogenation. Because effectively it's the same mechanism over and over again until you completely halogenate that methyl off the ketone. Repetitive halogenation. So I'm going to just use an R group for the ethyl. Okay, I'm going to call that R. I'm going to have my C double bond O, CH3. And I'm going to react this in base. So OH minus is added here. Pulls a proton off. This is my slow step. And it makes enolate anion. I'm not going to draw the resonance contributor because we've seen that before. So I'll just draw it as a carbanion because that's the reactive species. And then it reacts with I2, iodine. This is a fast step. And it creates RC double bond O, CH2, I plus I minus. Well, clearly this guy can now react, the R, C double bond O, CH2I. And because in this case the anion is stabilized by the electronegativity of the iodine, it's still the slow step, but this anion will form faster than the one above it. It can react with I2 as well. So we now have CHI2 forming here. We gain a kick out an I minus. And of course, the anion gets more and more stabilized. Still slow. In these two steps, I2 minus reacts with I. And the net reaction, of course, is R, C double bond O, CI3 plus I minus. Now the next step is unusual. Step 2. And it involves nucleophilic attack. See, OH minus isn't just a base. It's a very good nucleophile. Okay, so step 1 was repetitive halogenation. Step 2, nucleophilic attack. And so I can draw my R, C double bond O, CI3, and I can have hydroxide, OH minus, act as a nucleophile, attracted to delta plus on carbon of the carbonyl, and will form RCO minus. We'll have an OH down here, and we have a CI3. Now this is where things get interesting. What can happen, of course, is the O minus can dump electrons back and kick out the hydroxide, right? Or, more likely, is the O minus comes in, reforms its pi bond, and kicks out the CI3. Now you don't think as carbon as a good leaving group. Carbon's a terrible leaving group because alkanes, C minus, are extremely powerful bases. So why would you get CI3 minus leaving? Isn't that going to be a powerful base? Well, it's a fairly strong base. And remember, we've seen kicking out alkoxides before in hydrolysis of esters and other molecules, and we're going to see it again. Reforming the C double bond O can kick out pretty good bases. But alkane carbon minus carbanion is such a powerful base it would never leave. So why would CI3 minus be kicked out in this case? And the answer lies in the fact of the 3 electronegative iodines helping stabilize the negative charge. It is sufficiently weakening the basicity so that this can act as a leaving group. And when it does leave, of course we're in base, remember that. So base would deprotonate the H, making R CO2 minus. Okay. So there's why we get the carboxylate. Also, even though we're in hydroxide base, CI3 minus is a powerful enough base that there's enough water around that it's going to grab the proton and become HCI3, which is my iodoform. HCI3 will grab form, and as the proton is grabbed, and that's my yellow solid. The iodoform test is a very nice test for methyl ketones. If you shake up a methyl ketone with 3I2 and hydroxides, you see this yellow precipitate form. And so it's a nice test tube test for identifying, if you're given an unknown ketone, on whether there's a methyl group off of the ketone. But you do have to be careful with this reaction. Why is that? Well, if I rub out this top bit just for the moment, this reaction will work with secondary alcohols. What? Why would it react with an alcohol? Suppose I had CH3, CH2, CH, OH, CH3. Well, it turns out I2 in base can oxidize the alcohol to the ketone. And so you have to be careful. You have to remember, if you get a positive yellow precipitate, while it indicates that there was methyl ketone, that methyl ketone could have been formed from a secondary alcohol. It's just something to keep in mind when you look at this reaction mechanism. Turns out that if you repeat the reaction with Cl2 or Br2, you will form bromoform, okay, Bromoform is a clear liquid. Cl2 will yield chloroform, which is a clear liquid. Because of this, bromoform and chloroform are not useful as tests because there's no colored precipitate produced. But they do undergo identical reactions. What's nice about the iodoform is that it's a yellow solid. Okay. Well, that's it for this Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. And that's it for the alpha-halogenation reaction. Next lecture, we're going to investigate what happens if you conjugate an alkene bond with the carbonyl bond. I'm Dr. Brian Lloyd. As I said, this is my Scribblecast. I thank you for listening.